Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
So here we're going to say that the car is on the verge of sliding out, means that the force, the static frictional force, would be acting down the bank. We can then create some vector sum f, and this would be the vector sum of the static frictional force and the force normal. At this point, we can say that F is at an angle phi, which is measured from the vertical axis. And from the vertical axis, we can say that phi is going to be equal to theta plus theta sub s, where tangent of theta sub s would be equal to the coefficient of static friction, and we can say that theta would simply be the bank angle. At this point, we know that the vector sum of F and the vertically downward pull, which is simply equal to the weight of the car, must be equal to the horizontal centripetal force. So we can say that tangent of phi equals the centripetal force mv squared over r divided by mg. Let's cancel out the m's, and this is going to equal v squared over rg. So we can find the maximum speed and essentially isolate v. After isolating v, we can say that v max would be equal to the square root of rg tangent of theta plus arctan of the coefficient of static friction. This would then be equal to the square root of rg tangent of theta plus the coefficient of static friction. And this would be divided by 1 minus the coefficient of static friction multiplied by theta. So at this point, for part A, we can say that the given speed is roughly 17 centimeters. If we don't want the car to depend on static friction to keep from sliding out, and we want simply the down the back of gravity to be sufficient, then we can set mu s to 0 and obtain. And if we're setting mu s to 0, we can say that the V max would then be equal to simply rg tangent of theta. Again, this is for if we don't want the car to depend, car doesn't depend on mu s to keep from slipping. If we were to say that r equals 150 meters, this essentially means that we'd have to solve for theta. So theta would then be equal to v max squared divided by, or rather arctan of v max squared divided by rg. And here our v max would be equal to, again, roughly 17 meters per second. And therefore, if this is the case and we were to solve, we're getting that theta is essentially 11 degrees. So that would be our maximum angle such that the car doesn't slip and the car doesn't depend on the coefficient of static friction to keep from slipping. However, for part B, now we're going to analyze an unbanked curve. However, the relationship still stays the same. However, for an unbanked curve, theta equals 0 degrees. So we can say that V then equals the square root of RG tangent of arctan of the coefficient of static friction. This is simply equal to the square root of Rg times the coefficient of static friction. Given this, if we're going to solve, we can say that for the coefficient of static friction, we can say that the coefficient of static friction would then be equal to V squared over Rg. And again, if we plug in these values, we're getting that the coefficient of static friction would then be approximately 0.19. This would be our final answer for part B. That is the end of the solution. Thank you for watching.